Hello everyone and welcome to another lesson in this OpenGL series. Now in this lesson I'm going to cover with you lighting. Lighting is actually quite easy to work with. There are just a couple parameters you have to understand and yet you have to keep in mind while working with. First of all, we are going to use in OpenGL, we are going to work with in this class or in this course with per vertex lighting. Okay, so we are not going to use shaders, okay, and I'm going to describe you what does it mean per vertex lighting. So if I have, let's say, how I'm going to describe this, so let me go and make a small any object. So if I'm going to say this is my polygon, okay, oops, okay, apparently I didn't do it on a different layer, it doesn't matter. So if this is my polygon, and this polygon has, let's say, 3 faces, so if I grab my pen and describe 3 faces, so this is the first face, and this is the second and the third face. Okay, so if this is gonna be my 3 faces, so this is one polygon, second and third, so this is a huge or a big object, polygonal object. This is a vertex, this is a vertex, this is a vertex here as well as this one, as well as this one, and this one, and this one vertex, and this one as well as a vertex. If I got actually a small spotlight shining into here, okay, so this is a spotlight. Now if I'm talking about per vertex, not per pixel shading, means that I will have to test. OpenGL will go say, okay, this is my light, okay, does this vertex falls under this light? No. So this vertex doesn't fall under this light, so multiply the color of the light, which is in this place, since the file doesn't fall on it, is going to be 0. Multiply this color of the light by the color of the texture, whatever texture is going to be, a solid texture, 2D texture, whatever. Just multiply it by that one, and at the end, anything multiplied by 0 is going to be 0. So, eternal darkness. Next, is this pixel, or excuse me, this vertex falls under the light? No. So multiply the color of the light, which is black in this time, which is going to be 0, by the color of the texture, is going to be 0. 0 for the same thing here, 0 for the same thing there, and at the end you're going to get actually blackness here, blackness there. Now let's see, does the light falls under this vertex? No, because the vertex is not touched by that light. Blackness, 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 and blackness. So at the end you're going to get complete black, isn't it? Because the 4 vertices didn't touch the light, so at the end you're going to get eternal blackness. So your polygon technically is not going to be brightened up. So let me try to undo this. If we are in case, excuse me, let me just Control and Alt Z that. Okay, now in case that my spotlight got a little bit bigger, let's say it just got this area like so. So imagine that the vertex is actually falling under this light. So of course this is going to be black, this is going to be black, of course again this is going to be black because no touching, this is going to be black, no touching. But this guy falls under the light, so this is going to be brightened up, this is going to be brightened up, this is going to be brightened up, and this is going to be brightened up, and at the end you're going to get this square is brightened, is lit by the light. But the problem is, using that analogy, you will never actually get such a curvature of light. When you shine a flashlight on the wall, you're going to get actually some sort of circle, isn't it? But the problem is I will not get that circle because there are no enough vertices to describe it. So I have to describe like several of those vertices. So when the light is calculating, okay, this is a vertex, this is a vertex, so the light here, light is there. So at the end you're gonna get some sort of a jaggy kind of vertices, or jaggy kind of lighting. All right, this is because we are working with per vertex. If you are working with per pixel lighting, Per pixel lighting is what shaders are for. They are involve a lot of math. I don't want you really to go through that, so I will be quite satisfied with your projects if you're gonna deliver it for me in per pixel lighting, per vertex lighting, so you don't need to write your own shaders and so on. But in general, per vertex lighting, per vertex lighting, you have right now to sacrifice the quality of the object for this. I mean, for to make your application goes fast. But of course, once you sacrifice the quality, you're gonna sacrifice as well the lighting. But if you are would love to have the quality high and the lighting is nicely done or nicely shown to the user, you have to right now to make a lot of faces, a lot of vertices in order just for your application to be lit up correctly. So that's why people are using shaders or using something per pixel lighting. Okay, but for this course we're gonna use the per vertex lighting, and this is actually happening to be working quite well. Although there are a couple stuff that you have to understand, or a couple terminologies and parameters you have to take into account. First of all, a spot exponent. A spot exponent describes how fast the light is gonna fall off. So if you are focusing your flashlight, let's say here, the light is gonna be intense in that area, and it's gonna be starting falling off. It's gonna be easier and easier until it gets so gray at this part, and of course converted to be dark. Okay, so the light will not fall off, will not be constant with a constant intensity at the edges, but it's going to be a little bit grayish, or the light is going to be less intense on the edges until it goes to blackness. This is the spot exponent. The spot cut off, so you are describing, if you are talking about the cone of the spotlight, so this is the cone of the spotlight. Excuse me for the horrible cone here. So your light is actually shining from here. Your light is coming out of this cone like so. Okay. Now the cutoff, you are describing the angle in here. This is your cutoff. Okay. So if I say that this is gonna be 10, you are describing a cutoff, a whole diameter of 20. Okay, because this plus that, you're gonna get the whole this circle, so you're gonna get 20. If I put here 20, for that cutoff I will get actually 40. If I put even higher number, let's say 180, I'm gonna actually shine everywhere. Okay, this is for the cutoff. Attenuations, constant attenuation. That means that your light is gonna be following this equation. So K0 plus K1, or let's say K1 here, and this is going to be K2 D plus D for distance, by the way, plus K3 D squared. Alright, so for constant attenuation, if I'm going to look at the graph, and this is the intensity, okay, and this is going to be the distance. Alright, so if you are talking about attenuation, that means how fast or how much your light is actually traveling in z-axis. So if I am saying that you are standing here and this is a wall, and you are shooting a light, a spotlight here, your spotlight will never shine forever, like for like 10,000 kilometers or 20,000 kilometers. In fact, your light will be completely ineffective after several meters. Let's say if you are in a completely dark area, you're gonna be just shining your flashlight, let's say until, let's say, 20 meters ahead. But you cannot even shine that even far. I mean, this is going to have to be really completely dark areas just so you can see that far. But in general, your light is going to be stopping at a certain point. So this is what the attenuation means. So if I say constant, I'm describing some sort of a laser light, kind of a light that doesn't fall off by distance. So here I'm going to put 1. And for here I'm going to put 0 for both K's, so 0 multiplied by D is going to be 0. So when I'm saying that constant is going to be 0, whatever D is going to be multiplied, so it doesn't matter the distance, so it's going to be 0 all the time, and 0 all the time here as well. Alright, in case of I'm talking about linear, I'm going to put this to 0, and then I'm going to have the distance right now took in the equation, so I put the constants to 1, and the d is going to be like, say, whatever number is going to be. So whatever distance the light is going to travel is going to be always by 1 over kd, whatever you're going to be putting here, not 1 or 0.5 or whatever. So at the end you're going to end up with something, if I erase this, you're going to end up with something like so. Okay, so your light is actually falling, the intensity is actually falling, excuse me, the intensity is actually falling to the distance. Once the distance is going, the intensity just goes down and down and down. Okay, now if you, in case that you would love to simulate something real life, and I don't advise you to do so, a real life kind of light is going to be a quadratic attenuation, where you're going to put here 0 and you're going to put here 1, but you actually don't want to do that, because in this case you're going to have a little bit difficulty, because you have right now to go and crank up the light intensities, and a lot of numbers you're going to crank up really high in order just to compensate with the world, because right now you are simulating a real life lights, excuse me, a real life lights, which is going to be which is quite difficult I mean, real life lights, when you want to implement them in the in OpenGL or any 3D application, they are really difficult to simulate. They are not that easy. So as you can see here, the light is even falling faster than the linear. I mean, the linear is going to be somewhere like so. The quadratic is going to be even falling faster, even though it's going to be realistic. So you can actually, most of people escape from that by combining both of those two sometimes, in order to get something a little bit more realistic, without even cranking up the brightness of without cranking up the brightness of the light, or cranking up any numbers for that matter. There are also a couple stuff you have to understand. OpenGL only accepts, I mean, and most probably other graphics API, most probably, they only have 8 lights, so you have only 8 lights to work with, from light 0, so you have light GL enable light 0 to light 7. So GL light 7. Working with the mouse here again, so sorry for the handwriting. Hope this is clear. Alright, so from light 0 to light 7, these are the maximum numbers which you got, which actually your video card can handle in the same time. I mean, video card can handle calculating 8 light sources in the same time. It cannot go after, even above it. Even in OpenGL, you cannot enable more than 8 lights, because there are no more than 8 lights. In case that you say, okay, what about the games? You see that there are tens of lights in everywhere, but if you notice carefully, most of people doing a lot of tricks. They simply turn off the lights which you don't see and turn on the lights which you see. So at the end, when you are rotating your scene, you're gonna always active with at least, I mean, the maximum number you're gonna be active with is gonna be 8 lights, not even more, because they are simply the areas which you don't see. They just simply turn off the lights for that, and that's it. This is probably pretty much it. There are a couple, of course, light sources that you have to understand what are the types of light sources, and we consider ourselves done here. We just see the oops, sorry. We just can see here the code. We have point light, which is going to be simulating a light bulb. So you have a point. Oops, let me just. You have here a point, and the light is shining everywhere. So this is a point light. It's more like you can simulate with it a light bulb. A direct light is infinitely large. You can imagine it like a light that is emitted from infinitely large plane, infinitely far away. So so for example, let's say you have, if you would love actually to simulate such a thing, a direct light, you can think of it as the sun. You get almost parallel. I mean, in the sun you don't get the parallel lines. In fact, I mean, you get, I mean, since we are far away, so it seems to us as parallel lines of lights, or parallel beams of light. But in a direct light, actually you can get parallel lights. So you get lights is just shining from an infinitely large plane, really. So you get something like such a plane, infinitely large, and it's just simply you get the light shining from a specific direction. So you can see that as you can simulate it as the sun, or can you simulate it with a very far away object that is actually shining some certain light. This is a direct light. A spotlight in our case is more like the spotlights which you see in movies or in theater, where you have, for example, if this is the theater stand and these are the curtains, alright, so, and a small guy is standing here. That's quite interesting guy. So you have some sort of spotlight, so you have a light that is focused on a certain circle on him. You can simulate that with everything. A spotlight, like in theaters, as you can see here in this example, you can simulate a spotlight with a flashlight, which you can carry in your hand. This is one way as well to simulate it. So this is basically it. These are the three major three light type sources that you're gonna use, and mostly users or programmers are modifying these light types in order to achieve different effects, of course. Okay, let me go to the lighting test. So first of all, you're gonna download the library. I made it for you, so you don't need to worry about setting all these by your hand in the code. So you say GL lights. You of course import it here in the references. There we go. And in the initialization, please do not forget to write this line of code. So light.initialize lights, it has to be there. Without it, the application won't work, because when this function calls, I'm initiating all the 8 lights, but I'm turning them off. And then once you create a new object, I'm gonna take out 1 light out of the 8 lights which you have, and then you're gonna start using them. So you create a new light and you say it's gonna be a spotlight. You say this is the diffuse part of the light is mean that you are describing the intensity and the color of my light. Setting the position of the light source, setting the cutoff is 20. This is in my case gonna be like 40, the full diameter. And exponent is the how fast the light is gonna be falling off from the center. Now there are a couple of parameters here. Specularity, for example, this is right now describing the materials for my object, which is gonna be when it's gonna be rendered. So specular highlights, for example, if you carry on a metallic ball, you get like a small shining point, a white point, or yeah, the brightest point in that metallic ball is my specular highlight. Emission, it means that the object can emit light without the need of any lights at all. So you can, I don't know how you can imagine it like the phosphor kind of, you know, like in your watch, for example, you get those handles or those pointers, sometimes they shine in the dark. So you can say that the emission of these objects, let's say, is going to be 1, 1, 1, 1. And shininess, how much shiny the object is going to be. And then in the material FV, F is for float and V is for vector. A vector means that you're going to pass an array of whatever size is going to be. So let's say in shininess, if I say 15, it's going to be, as far as I remember, it's going to be 15,000 for all the way, for all the rest of the array elements right away. In case if you wanted to specify by yourself, you can just type it like so. Alright, so here a message box just for testing, just for debugging purposes. I will show it to you in a second. And please do not forget, once you load identity, you have to do this, because once you have to update your light positions, because once you start manipulating your scene or rotating your objects or rotating your scene, in fact, you're gonna get your lights has to be updated or accordingly. So you have to always update the light positions with you. And I believe this is it. I'm right now pushing matrix and popping matrix for rotating a sphere some sort of, but let's see what's gonna happen here. So this are the testing lights. So this is 7 lights available to use. 1 is used, so we have in total 8 lights. And this is my sphere. So I got actually a a light shining from above, by default, please remember, by default you have the spotlights. By default they shine to down, so you can imagine it like shining to negative y, for instance, or something like that. So when you put your light source, it's just shining from above to down, downwards, like the light which is above your head in your room, for example. It is positioned upwards and shining down towards you. In case if you positioned your light somewhere else, you have the function which is called the light dot set spot direction, and then you're going to specify the x, y, and z where your light is going to look at. And as you can see here, I got my sphere. It's lit up from the top. The blue which you see is my specular highlight. If you didn't notice, what is my specularity? As you can see here, I put here as blue, and so that's why this is actually what is the effect of light if reflecting. So this is like the specular highlight which I get from once the light is bouncing off the sphere. So I get some sort of interesting metallic effect. So the sphere is white, but when the light is reflecting off it, it gets an interesting effect here. And as you can see here, you see how the light is flashing, like it's not smooth, you know. As you can see here, it's a little bit jaggy on the edges. This is because I'm using here per vertex lighting. If I use something a little bit dense, let's say 100 by 100, let's hope it's gonna be handling it fast, at least for this records. As you can see, watch this. You see how the specular highlight is looking like? It's like metallic, nice metallic kind of reflection, and you get a really cool lighting. You see, it's just very smooth, and this is because I cranked up the number of vertices. Now please do not do that. I mean, this is done just to show you what I'm talking about. This is the specular highlight of my sphere, as if it was like metallic blue reflection coming out of the white sphere. This is quite interesting effect, by the way. So this is it. I would love to show you as well the code for that. So the texture, the lighting code, I mean, you can actually forget about this. Here is the updating the lighting positions and the spot direction as well, by the way. As you can see here, I'm updating the spot direction. And set attenuation, here you go. Here are a couple functions. Set attenuation, just to set if it is going to be constant or linear. I mean, if you're going to set that numbers, just pass here, let's say 0. I mean, if you're going to make it constant, 0, 0, and 1. So you're going to pass 0, 0, 0, 0, and 1. So it's going to be 0, 0, and 1, and so on and so forth. Specularity, specular highlight, if you want to give your light actually the specular kind of how can I say, kind of effect. Diffuse here for the color, so RGBA, and probably that's it. Set the ambience of the light, how the light is actually distorted in my scene. Here's the attenuation, I already covered that. Spot direction, so you pass the X, Y, and Z. Position of the light, updating the light. So this is it. Initializing light. As you can see here, I just made a for loop and I enabled every light which I have in my OpenGL libraries, and that's it. This is pretty much it. All right. From now, I believe right now, by the end of this lighting lesson, I encourage you that you go by yourself and try right now to implement some of your own kind of ideas and applications using OpenGL. So here, I believe this is it for this lesson. Then see you in the next lessons.